This online tutorial is about the Lux-Flood acid-base definition and theory. The Lux-Flood acid-base theory was proposed by Lux in 1939 and then extended by Flood in 1947. Based on the Lux-Flood acid-base theory, an acid is any chemical species capable of accepting an oxide ion from a base, and a base is any chemical species capable of donating an oxide ion to an acid. In other words, a Lux-Flood acid is an oxide acceptor and a Lux-Flood base is an oxide donor. So we have the Lux-Flood acid-base theory, based on which acids are capable of accepting an oxide ion, a 2- ion, from a base. That is, there are an oxide acceptor. On the other hand, bases are capable of donating an oxide ion. They are oxide donors. For example, we can consider the reaction between CaO, calcium oxide, and SiO2, silicon dioxide, which can happen at molten inorganic mixtures at high temperatures. This reaction yields CaSiO3. It is good to know that this reaction is very important in elimination of silicon impurities in steel making, in steel industry. In this reaction, calcium oxide donates an oxide ion to silicon dioxide, and silicon dioxide accepts that oxide ion. Calcium oxide becomes Ca2 plus, and silicon dioxide becomes SiO3 2-. We see that in this reaction, calcium oxide acts as an oxide donor. So we can consider calcium oxide as a Lux-Flood base here. On the other hand, in this reaction, silicon dioxide acts as an oxide acceptor. So we can consider silicon dioxide in this reaction as a Lux-Flood acid. And the reaction with each other yields a salt. Generally, oxides of metals like calcium oxide, CaO, ferrous oxide, FeO, magnesium oxide, MgO, and so on, are Lux-Flood bases. While on the other hand, oxides of non-metals like SO3, CO2, and so on are Lux-Flood acids. Here it is important to note that there exists an analogy between Brensted-Lowry acid-base theory and the Lux-Flood acid-base theory. Based on the Brensted-Lowry acid-base theory, an acid is a proton donor, a base is a proton acceptor, and we can consider conjugate acid-base pairs where a conjugate acid and a conjugate base are converted to each other by adding or removing proton, or protonation and deprotonation. So based on the Brensted-Lowry acid-base theory, we can consider reactions like this. On the other hand, based on the Lux-Flood acid-base theory, an acid is an oxide acceptor, a base is an oxide donor, and we can consider conjugate acid-base pairs where a conjugate acid and a conjugate base are converted to each other by adding or removing an oxide ion. So, based on Lux-Flood acid-base theory, we can consider this. Based on the Brensted-Lowry acid-base theory, in an acid-base reaction, we have transfer of H plus from acids to bases, yielding their conjugates. So, based on Brensted-Lowry acid-base theory, we have this. Similarly, based on the Lux-Flood acid-base theory, in an acid-base reaction, we have transfer of O2 minus, this time from bases to acids, yielding again their conjugates. So, based on the Lux-Flood acid-base theory, we have this. Where here, we usually have their conjugates in the form of a salt, like this reaction. It is easy to see that there exists an analogy between these theories. However, they are different in nature. Brensted-Lowry deals with transfer of H plus and emphasizes proton as the principal species in acid-base reactions, while Lux-Flood acid-base theory deals with transfer of O2 minus in acid-base reactions and emphasizes O2 minus as the principal species in acid-base reactions. Because of this, while Brensted-Lowry acid-base theory is useful for hydrogen-containing compounds, Lux-Flood acid-base theory is useful for oxygen-containing compounds like oxides and salts of oxyacids at their molten forms at high temperatures. For example, acidic and basic anhydrides are among good candidates to be analyzed by Lux-Flood acid-base theory, where acidic and basic anhydrides are compounds produced by removal of water from common acids and bases. For example, CaO, calcium oxide, from CaOH2, calcium hydroxide, SO3 from H2SO4, and so on. Historically, at first Lavoisier considered the element oxygen as essential part of acids. He named oxygen as acid former. Later, Berzelius proposed that acids are oxides of nonmetals and bases are oxides of metals. But later, based on works of scientists like Liebig, Arrhenius, Brewster, and Lowry, acid-base chemistry shifted from oxygen-containing compounds to hydrogen-containing compounds. As scientists found theories like Brewster-Lowry acid-base theory much more useful for analysis of acid-base reactions in solutions of solvents like water. However, there are difficulties on applying other acid-base theories to oxides. While this is not the case with Lux-Flood acid-base theory. The area of application of Lux-Flood acid-base theory is limited to oxides and salts of oxyacids at their molten forms at high temperatures. This is important in some areas like electrochemistry of molten inorganic mixtures, geochemistry and properties of salts, and so on. So, Lux-Flood acid-base theory is limited to some specific areas. But in those areas, it is a very handy tool and it is very useful. Unfortunately, in those areas, Lux-Flood acid-base theory has the disadvantage of not considering analogous reactions of S2- sulfide ion, F- fluoride ion as acid-base reactions. In molten inorganic mixtures, we can have transfer of S2- sulfide ion, F- fluoride ion, and so on, very similar to transfer of O2-. While Lux-Flood acid-base theory considers transfer of O2- as an acid-base reaction, doesn't assume the same for other analogous cases, and this can be considered as an disadvantage for this theory. Here it is also good to talk about some interesting facts suitable for this discussion pointed out by Flood in his article in 1947. The first one is the fact that salts of chromate can indicate how acidic or basic a glass is. If a small amount of salts of chromate is added to a glass at its molten form, we can have this chemical equilibrium. If glass is acidic, as Lux-Flood acids are oxide acceptors, there is less of oxide ion here, so this chemical equilibrium is shifted to the right, and we will have more of Cr3+. On the other hand, if glass is basic, as Lux-Flood bases are oxide donors, there will be more of O2-, and this chemical equilibrium is shifted to left, producing and increasing CrO4 2-. In the case of an acidic glass, we have more of Cr3+, And in the case of a basic glass, we will have more of CrO4 2 minus. After cooling, CRT plus makes glass green, while CrO4 2 minus makes glass yellow. So we see that in the case of an acidic glass, the color will be green, while in the case of a basic glass, the color will be yellow. This chemical equilibrium also depends on the partial pressure of oxygen, and there exist other better methods in this regard. But this is very interesting to see how the color of glass may change based on how acidic or basic it is. Another fact pointed out by Flood in his article in 1947 was about the change of coordination number of atoms upon transfer of O2 minus. Coordination number of a specified atom in a chemical species is the number of atoms directly linked to that specified atom. Flood pointed out that for atoms with high ionization energies, we usually have an increase in coordination number upon transfer of O2 minus. For example, consider these reactions. In this reaction, the coordination number of sulfur atom increases from 3 in SO3 to 4 in SO4 2 minus. In this one, the coordination number of carbon atom increases from 2 in CO2 to 3 in CO3 2 minus. So we see, in the case of the atoms with high ionization energies, we usually have an increase in coordination number upon transfer of O2 minus. On the other hand, in the case of the atoms with medium ionization energies, Flood pointed out that the coordination number don't change usually upon transfer of O2 minus. For example, consider these reactions. Based on Lewis structures, we can see that in these reactions, the coordination number of atoms don't change. In both sides of this reaction, the coordination number of the boron atom is 3. And on both sides of this reaction, the coordination number of silicon atom is 4. It is important to note that in the structure of silicon dioxide, the coordination number of silicon is 4 as it is connected to 4 oxygen atoms by 4 single covalent bonds. It has a network covalent structure. Finally, in the case of the atoms with low ionization energies, like atoms of metals, we don't have covalent bonds, like those of these ones. We have ionic bonds. For example, in the case of magnesium ions, we will have this ionic phase. So, Flood categorized atoms based on their relative ionization energy. Those with high ionization energy usually see an increase their coordination number. Those with medium ionization energies usually don't see any change in their coordination numbers upon transfer of O2 minus. And in the case of those with low ionization energies, we have ionic phases. This is the end of this online tutorial. I hope you find it useful.